So let's look at the problem of searching for a value in an array. So in general, the search problem is to find whether a value k is present in a collection of values A. Now in our case, we will think of A as generally as a sequence of values. And moreover, we'll also assume that the sequence is something like integers where we can talk of one value being less than another value. So the values can be ordered with respect to each other. So we already saw that we can keep such sequences in two different ways, as arrays and as lists. And depending on whether we keep it as arrays or lists, the way we can access the elements is different. So the first question we might ask is whether searching makes a difference in a list versus an array. And the second question we might ask is there some importance to how the values are arranged in this sequence? Does it help if they are in ascending or descending order? Or does it not matter? Is it equally the same to search for something in a randomly collected collection of values, randomly ordered collection of values, or when it is structured in some particular way? So in the unsorted case, we have no choice basically. We have a sequence A which runs from 0 to n minus 1. So we must look at all the values because we have no idea where k may be. So a systematic way to do it is to start with the position 0 and just scan all the way to n minus 1. So we have this loop here which scans, okay? And the scan either terminates when you reach the end without finding it, or when at some position I we find that ai is equal to k. And then depending on that, we either say that it is found, in which case we return the position, or we have reached I equal to n, which means we have gone beyond a n minus 1, and so we return not 1, minus 1, which is an invalid position to indicate that it's not found. So we saw before that the worst case actually happens when k is not an element of A. That k doesn't come in A, we have to scan A0 to an minus 1 in order to determine that k is not there because we have no evidence in advance which position it's likely to be at. So this means that in the worst case, searching for an element in an unsorted array takes linear time. And of course, it doesn't matter now whether it's an array or a list, because in a list we could also in linear time start from the first element and follow the links all the way to the end. In an array, we start with A0 and go all the way to an minus 1. Both of them take linear time. On the other hand, if the sequence is sorted, and in particular if it is an array, we can be a little more intelligent. Right? So what we know is that the values are, say, in ascending order. So if we probe the value in the middle, okay, and check this, is this equal to k? Right? If the value that we have is equal to k, of course we have found it. If it is smaller than the value here, then we only need to search in this half. Okay? And if it is larger, then we need to search in this half. Now this is something that we intuitively do all the time. This is how we look for, say, words in a dictionary, or when we play 20 questions. Right? We try to ask questions about the age of a person, then we'll say, is this person less than 40, is this person greater than 65, and so on. Right? So this is something we know intuitively, but we can formalize it. Right? So we take the midpoint of the range we are searching for. If the midpoint is the value that we want, we have found it. Otherwise, depending on the value we are looking for and what the value is at the midpoint, we search either the bottom half or the top half. So this has a name, which many of you may already know, and this is called binary search. So here is a simple recursive algorithm for binary search. So in general, it searches an array. Remember that when we do this search, we might be searching different segments depending on how far we have progressed in the search. So in general, binary search takes a value k to search an array and two endpoints, left and right. And just to make sure that we get everything right, we will have the convention that it searches from the index L to the index R minus 1. That is, it searches from L to R, but not including R itself. So now if L and R are actually the same, then we have an empty array, right? Because L to R minus 1 is actually something where there are no elements in between. So we say we haven't found it. So when the interval that we are searching for becomes empty, the array definitely doesn't contain the value we are looking for. Otherwise, we compute the midpoint between L and R by taking the sum and dividing by 2, and because this might be an odd number, we use integer division. Now we examine, at this point we have found the midpoint, right? So now we examine if the value that we want is there at the midpoint. If so, we return true. Otherwise, if the value that we want is smaller than the midpoint, then we go to the left. Okay, and if the value that we want is bigger than the midpoint, then we go to the right. Right? So this either goes from left to mid minus 1, or mid plus 1 to right. In other words, we exclude mid from our search, right? So the first case runs the search from left to mid minus 1, because that's our assumption. If we call it with mid, it goes to mid minus 1. This one starts at mid plus 1 and goes to right minus 1. So the original thing was from left to right minus 1, and we have now excluded mid from this, and we have also halved the interval to search. So the crucial advantage of binary search is that each step we halve the interval to search, and at some point we will reach 1, and then when we halve 1, we'll get an interval of size 0, and so we will get an immediate answer. Right? So we can write, as we saw for such recursive functions, we can write what is called a recurrence. Right? A recurrence is just an expression for the time in terms of smaller values of the same expression. So the base case is that when we have T of n, we mean the time taken to search in a list or an array actually of size n. Right? So T of 0 is 1. So if we have an empty array, we have nothing to do. And T of n in general is one step to find and compare. So this 1 is actually a constant number of steps to compare with the midpoint and decide to go up, down and all that. So those operations, plus the time taken to search whichever half we focus on, the left half or the right half. Remember that if we look at the left half, we are never going to look at the right half again. Okay? So one way to solve such a recurrence is to unwind it. Right? So we have Tn is 1 plus Tn by 2. So we take n by 2 and we do n by 2 divided by 2, and rather than write it as n by 4, we will write it as n by 2 squared. Okay? And this is because now if I do it one more time, it will be 1 plus 1 plus 1 divided by 2 cubed and so on. So in general, you can see that if I do it k times, then I'm going to have k ones here. Okay? So if I do 3 times, I'll have 1 plus 1 plus 1 plus t n by 2 to the 3, 4, or 4 plus t n by 2 to the 4 and so on. So after k steps, I have k plus t of n by 2 to the k. Now when n by 2 to the k becomes 1, at the next step I'm going to get t of 0. Right? So when does this become 1? When n is 2 to the k. In other words, when k is log 2 of n. Right? So when I get log 2 of n, then this has become t of 1. Okay? And at the next step, this is going to become 1 plus t of 0. So this is going to be log n ones, and so overall the complexity of binary search is just order of log n. Right? So we have gone from a linear search in the case of an unsorted array to a logarithmic search in the case of a sorted array. So we mentioned in the previous unit about arrays and lists that things that work on lists may not work on arrays and vice versa. So here is an example of something which works only for arrays. Right? The idea of looking up the midpoint and then going left works only if you can find the midpoint at constant time. If you have to spend time looking for the constant for the midpoint, then you cannot get this recurrence anymore. It's not going to be 1 plus t of n by 2, but it's going to be n plus t of, or n by 2 plus t of n by 2, and then we'll actually get a linear. So binary search for a list will actually turn out to be linear because of the time it takes us to go to the midpoint. Right? So this works only for arrays. But really the remarkable thing about binary search is that by only looking at a very small fraction of the sequence, we can conclude that an element is not present. So we know, for instance, that 2 to the n, 2 to the 10 is 1024. So if I give you 1,000 values, okay, we can look at 10 or maybe 11 and say that something is not there. So the overwhelming number of values we don't even have to look at in order to decide whether a value is there or not, and this makes binary search a truly remarkable procedure if you think about it carefully.